Alright gang, here we go. This is for Chem 2, Unit 9. We're going to do a practice problem here using kinetics where we are given a set of data here, alright, and we're going to try to answer these questions. This is a really typical kinetics type question, alright. So we've got this balanced chemical reaction where we've got nitric oxide reacting with hydrogen to form nitrogen and water, alright. And the first thing they ask us to do is determine the rate law. Now we know that the rate law generally is going to have this format, right? It's going to be rate is equal to K, and then it's going to always be multiplied by the concentrations of the reactants, all right? But remember, they're raised to the power, and that power is the order of the reaction in regards to that reactant. So we have to find this X value and this Y value. Alright, so in order to do this, we're going to look at these experiments and compare trials and their rates. And so, for example, from experiment 1 to 2, the nitrogen monoxide here was kept at the same concentration, and then the hydrogen was doubled. And then we can use that, so the only thing that could have affected the rate between these two experiments was the concentration of hydrogen. So we can use that to determine the order, and then we can do the same thing from experiment 1 to experiment 3. Alright, we're looking for how does it change with regards to nitrogen monoxide, because the nitrogen monoxide changes from experiment 1 to 3, but the hydrogen remains the same. Alright, so let's just do experiment 1 to 2 real quick. So essentially what we're doing is that we know that rate of reaction 2 over the rate of reaction 1 will be equal to the concentration of H2 over the concentration of H1 raised to some power, and because I said it was y over here, we'll use y here. Now we're just going to plug these guys in, and we can plug in individual numbers, or we can just figure out what these ratios are. So if we took rate 2 divided by rate 1, it's pretty easy to see that we just get 2. So 2 would be equal to, alright, so this is the concentration of H2 divided by the concentration of H2 and a reactant 2. Sorry, this is confusing, my bad. H2 and the reactant 1. There we go. So H2 of experiment 2 and then H2 of experiment 1, and you can see again we'd get 2. Alright, and so our Y value would have to be 1. So Y would be equal to 1. Alright, so that's easy. So our rate law would be equal to K, and we still haven't figured out nitrogen monoxide yet, so we're going to leave that one alone. But we know for sure H2 is 1. Alright, so there's that guy. So we can also do the next one here. So the next one we're going to be looking at experiment 1 to 3. Alright, because this is where we keep H2 the same in experiment 1 and 3, and then NO is doubled. Alright, so for experiment rate of 3 over rate of 1, and that's going to be equal to the concentration of NO in experiment 3 over the concentration of NO in experiment 1 raised to some X value. All right. So we can see if we go from 3 to 1 right here that it was quadrupled, right? So our rate quadrupled. All right, so we could, and if you don't see that right away, you can simply just divide them. Take this number here, divided by this number here, and you should get 4. All right, and then we already established that these concentrations were doubled. All right, so it's easy to see that because of this, your X value would have to equal 2. So it's a second order with respect to NO. All right, so this would be our rate law. All right, so this is our rate law for this reaction. All right, that's pretty easy. So it's third order overall, just to review a little bit what we've done in the past. Alright, so then the next thing here says calculate the rate constant. Well, to calculate the rate constant, all we have to do, since we have the rate value, we're just solving for this K value. So our K, so this would be for part B here, our K is equal to our rate divided by the concentration of NO squared times the concentration of H2. Alright, and then we just simply pick any reaction or any experiment and just plug things in. So we could just do experiment 1 because it's on top and it seems nice. So we'll do 1.23 times 10 to the minus third, alright, over NO squared, so that's 0.1 squared times 0.1. Alright, and then we just plug that into our calculator. Don't forget to keep your denominator in parentheses here. Okay, otherwise you'll look like a fool because you set it up right, but you don't know how to run a calculator. 1.23 e to the negative third divided by 0.1 squared times 0.1. And I got 1.23. And just to make sure that's what I got earlier. That's exactly what I got earlier. All right, so that's that. That's good. 1.23. But now we got to think about our units. All right, so what would our units be for this guy? Well, just to recap what we talked about in the last video, we know that our rate law has to have the rate of our reaction will always be in molarity per second. That's also what's written here in our table right here, so that's good. All right, so molarity per second, those units here have to equal whatever our units are for our K value. Okay, and you got to figure out what the numerator and the denominator is, times, so concentration's always in molarity, so there's a molarity squared, and there's a molarity, right, for the H2. All right, and those are being multiplied together. So we got to figure out, well, what would this be? So this whole thing multiplies to equal this side over here. Well, we've got molarity squared too much over here, so we'll put a molarity squared in the bottom, and then we also need a seconds. All right, so it would be 1 over molarity squared times seconds. All right, so that would be our rate constant. All right, for this reaction. All right, and then for part C, it says calculate the rate when concentration of NO equals that, and H2. Well, this is easy. We know the formula to calculate rate. It's just right here, right? It's the rate law. Rate equals our K value, which is 1.23, all right, times the concentration of NO squared, right? So that would be our 0.05 squared times the concentration of H2, which is 0.150. All right. So we take our 1.23 times 0.05 squared times 0.15, and we get 4.61 times 10 to the minus fourth. How many sig figs? Each of those guys have, or the concentration of NO has 2 sig figs, so we'll just leave it there. So it'd be 4.6. 4.6 times 10 to the minus fourth. 1.23.05 squared times. Okay, all right. Times 10 to the minus fourth. And the units here, it's rate, so it would be molarity per second. All right, so that's it for using this kind of problem. They get, slightly more complicated or less complicated depending on what rate law you get, and so on and so forth. And so then as we move forward here, we're going to talk about, well, what does it mean specifically if we have a zero order, a first order, a second order reaction? And this is, this stuff is difficult, but it's pretty easy. As we move forward here, we start having to worry about some more complicated math to keep track of our rates. All right, so stay tuned, keep your hats on, and I'll see you on the flip side.